Now, notwithstanding its current state of disfavor overall in the chemical industry, I believe that catalysis still has a bright future and an important role to play, but that its thrust will be quite different. In the recent past, when growth rates were high, or at least respectable, it was possible to justify a good deal of catalytic research on the basis of incremental improvements and incremental benefits. For example, for a world-scale plant of £1 billion per year, a reduction in manufacturing cost of 1 cent per pound provides an annual payoff on the order of $10 million. This is enough to pacify or perhaps at least tranquilize the corporate financial wolves. With low growth rates and general continuing overcapacity, however, the situation differs. Incremental advances are no longer acceptable. Major changes are needed. Discontinuities in existing technology are required. This is a very different ballgame for everyone. For management, it requires a much higher level of risk and patience than most managements are prepared to accept or are comfortable with. For the scientists, it requires a much higher level of creativity, originality, and challenge. Now, in trying to address a specific need or opportunity for radically new catalytic chemistry, how does one proceed? I believe that there are a couple of myths around. One of these is that it is now possible to scientifically design new catalysts as a result of the great insights being provided by advanced instrumental techniques in surface science or in computer science. This is simply not true. These surface and computer science techniques have very much, greatly increased our ability to characterize catalytic materials and processes, but we are still very far away from being able to a priori design a catalyst, that is, to prescribe its chemical composition in order to catalyze a reaction in some significantly new way. Now, the most progress that I'm aware of in a priori design is in the area of homogeneous catalysis, and that is the area that I think most likely will enjoy the greatest further progress, at least in the near term. Now, in the remainder of my talk here, I'd like to consider the future of catalysis in terms of what new industrial developments can we expect in the future. These will be the result of either being able to do something not now practiced commercially or being able to significantly improve some existing process. Stated another way, I'll try to identify some of the unsolved problems or limitations of current industrial catalysis and, in a few cases, to suggest directionally what new approaches might be worth considering. Now, we see here the three key elements of any catalytic process, namely the raw materials, the feedstocks, the catalyst, and the products. And in attempting to think about future developments in chemical catalysis, one convenient way is to consider these three basic elements and to project possible new developments that can be stimulated or driven by each of them. And today, in my talk, I'll just deal with the first two. First, let's consider the area of feedstocks. Methane has always been an attractive low-cost feedstock in those areas of the world where it's abundant and accessible. It's used to produce methanol, ammonia, hydrogen, and synthesis gas. Now, very obviously, one of the major unsolved challenges for catalysis would certainly be a catalyst that promotes the one-step direct oxidation of ethane to methanol. If such a catalyst were developed, it could have far-reaching implications. It might lead to the production of synthesis gas via methanol dissociation rather than the reverse process which we practice today, namely the formation of methanol from synthesis gas in a thermodynamically limited, low conversion process which employs a large amount of recycling, both energy and capital intensive. The synthesis gas, in turn, is made via endothermic steam reforming of methane in many cases. Other uses can be seen for methanol produced via direct methane oxidation and synthesis gas derived from same. For example, synthesis gas could be shifted in the usual way to produce large quantities of lower cost hydrogen. Recently, we've seen some new results in the literature that signal both increased activity and progress in selective methane oxidation, and some of that is being reported at this symposium, while at this conference here. While they are a long way from practicality over previous results, we should take heart in the knowledge that there are enzymes which can oxidize methane to methanol with very high selectivity. Personally, I believe that when practical systems are developed for the selective oxidation of methane to methanol, they will employ organometallic complexes at relatively mild reaction conditions rather than metal oxides at high temperature. Recently, we are also seeing new research results in which the products of direct methane oxidation are not methanol, but